hole opened in the sun, a real one. A dark, gaping void in our star's outer atmosphere pointed directly at Earth. Right now, a river of charged particles is crossing 93 million miles of space at 370 miles per second. It will hit. We'll cover how this hole was spotted, why it could knock out GPS and power grids, what makes auroras glow green versus red, and why scientists just discovered our forecast models have been wrong about the sun this whole time. If you find this useful, a like and subscribe means the world. Now, let's go. Something happened on Wednesday, May 13th, 2026. A hole opened in the sun. NASA's cameras caught it. A massive dark void sitting in the northern part of our star's outer atmosphere, staring straight at Earth. And within hours, space weather agencies around the world started issuing warnings. Now, before your brain jumps to disaster movie territory, here's what's real. This hole is confirmed, the warnings are confirmed, and what's coming from it is already on its way. But to understand why this matters, you need to understand what you're actually looking at. When most people picture the sun, they picture fire, a giant ball of burning gas, uniformly bright, uniformly dangerous, and that picture is mostly right. The sun's surface blazes at around 10,000 degrees Fahrenheit. Its outer atmosphere, called the corona, burns even hotter, reaching millions of degrees. The whole thing glows white and violent in every direction. So when NASA posts an image of the sun and there's a massive pitch-black region sitting on it, your first instinct is, something is wrong. And you're right. Something is different, but not in the way you'd expect. That dark patch isn't burned out. It isn't dead. It's actually one of the most active, most dangerous regions on the entire star, because of what it's doing, not what it's missing. Here's the key. The sun's corona is held together by magnetic field lines. Think of those lines like invisible rubber bands stretching out from the sun's surface. In most places, those bands arc upward, loop around, and snap back down to the surface. They trap the hot gas, the plasma, the energy. That's what makes the corona so bright and dense in most regions. In a coronal hole, those bands don't loop back. They stretch outward into space and keep going. They never return. And because there's no loop to hold the plasma in, the hot gas just pours out straight into the solar system, like water spraying from a broken hose with nothing to stop it. That open configuration is why the region appears dark in ultraviolet images. Less trapped plasma means less heat. Less heat means less light. So in NASA's cameras, it shows up black against the blazing brightness of everything around it. The hole detected on May 13th measured enormous. Large coronal holes have been measured at widths of nearly 500,000 miles across. For scale, you could line up more than 60 Earths side by side and still not reach from one edge to the other. And this one was sitting almost exactly at the sun's equator. That detail matters more than the size. A coronal hole at the poles shoots its wind up or down, out into empty space, mostly missing Earth. A coronal hole near the equator points its stream like a laser aimed directly along the flat plane of the solar system, directly where Earth orbits, directly at us. Scientists at the Space Weather Prediction Center confirmed the positioning on May 13th. The stream it was producing was already aimed at Earth. The question wasn't whether it would arrive. The question was how hard it would hit. And here's what made forecasters nervous. Between the hole and Earth, something was building in space. A compressed wall of particles invisible to the naked eye racing ahead of the mainstream. It was going to arrive first. And whatever it did when it got here would set the tone for everything that followed. Here's something that should break your brain for a second. The sun's surface burns at around 10,000 degrees Fahrenheit. Its corona, the outer atmosphere floating above that surface, burns at over 1,000,000 degrees. Scientists still don't fully understand why the atmosphere is hotter than the surface underneath it. That's a confirmed mystery that no one has solved yet. But inside this already scorching system, the coronal hole is the coolest, least dense region of all. The place that looks the most threatening is actually the least energetic part of the outer atmosphere. And that's exactly why it's so dangerous. In normal parts of the corona, magnetic loops trap plasma like a pressure cooker, keeping it hot and dense and bright. When you remove the lid, the pressure drops, the plasma escapes, temperature and density fall. What's left behind is a thin, dark, open channel, and everything that was trapped is now flying outward into space at speeds that would circle the Earth in under a minute. This is confirmed science. The open magnetic field geometry of coronal holes has been studied for decades. NASA's Solar Dynamics Observatory watches the sun in 10 different wavelengths of light, including extreme ultraviolet, which is the range that makes coronal holes visible. Every 12 seconds it takes a new image. That means in the 2 days between detection and impact, the observatory photographed that hole thousands of times. What those images showed is a region that looks calm, almost peaceful, a quiet dark patch against a sea of white. And that's the trap. The calm surface of a coronal hole hides the fact that it's actively firing a stream of particles at 1.5 million miles per hour into the solar system. Now here's something that surprises most people. Coronal holes aren't rare, they're actually normal. The sun almost always has coronal holes near its poles. They're the source of the background solar wind that constantly fills the space between the planets. You are inside that wind right now. Earth is always swimming through it. What makes this hole different is the location and the timing. Polar coronal holes aim their streams toward the top and bottom of the solar system. They mostly miss Earth. But equatorial holes, holes sitting near the sun's middle, they aim straight along the plane where all the planets orbit. Earth sits right in that plane. On May 13th, the hole was confirmed in the equatorial region of the sun's northern hemisphere, perfectly positioned, perfectly aimed. And here's the part that space weather forecasters pay close attention to. The sun rotates. One full rotation takes about 27 days. So a coronal hole near the equator doesn't just fire once, it sweeps past Earth like a garden sprinkler, returning to the same position roughly every 27 days. That means this isn't necessarily a one-time event. Scientists already labelled mid-June 2026 as a date to watch, because if this hole survives another solar rotation, it sweeps back around and aims at Earth again. Confirmed persistence of coronal holes can last weeks to months. Whether this one stays open that long is still unknown, but right now, what matters is the stream it already fired. Because that stream doesn't travel alone. Something is riding in front of it. Something that forms when fast-moving solar wind crashes into the slower wind already filling space. And that compressed wall of particles was expected to arrive at Earth first, hitting the planet's magnetic field like a battering ram before the mainstream even arrived. In orbit above Earth, a satellite stares at the sun every 12 seconds, every day, every year. It never blinks. NASA's Solar Dynamics Observatory, launched in 2010, watches our star in 10 different wavelengths of light simultaneously. Most of those wavelengths are invisible to human eyes. Extreme ultraviolet, X-ray frequencies, ranges of light that pass through Earth's atmosphere without a trace, which is exactly why the observatory has to sit in space to catch them. And it was this satellite's cameras that made the May 13th detection possible. In extreme ultraviolet imaging, the sun looks completely different from what you'd see with your eyes. The bright plasma regions glow in brilliant false colour. The magnetic loops that trap energy stand out in vivid detail. And coronal holes appear as sharp, dark regions, unmistakable against the luminous background. When the automated detection system flagged the hole on May 13th, it flagged the location too. Northern hemisphere, near the solar equator, facing Earth. That combination triggered an immediate chain of events. Space weather agencies on multiple continents started running models. The Space Weather Prediction Centre upgraded its storm watch. The UK's Weather Office issued Aurora forecasts for Scotland. Monitoring networks that watch power grids and satellite systems went on alert. All of it started from a dark patch in a photograph taken from orbit. But the Solar Dynamics Observatory doesn't work alone. a satellite called GOES-19, operated by the National Oceanic and Atmospheric Administration and sitting in orbit above North America, also identified the structure independently. Multiple instruments, multiple agencies, multiple confirmations. This was real. Now here's where the detection story gets genuinely strange. The coronal hole was visible days before its stream arrived at Earth. The solar wind takes 2 to 3 days to travel from the Sun to Earth, crossing 93 million miles of empty space. That travel time is what gives forecasters their warning window. 2 to 3 days sounds like a lot, and for Aurora watchers hoping to plan a road trip north it is. But for power grid operators and satellite companies, 2 to 3 days is uncomfortably short. They can see the storm coming, they can't stop it, they can only prepare. And preparation looks different depending on what you're protecting. A grid operator might reduce load in vulnerable regions. A satellite operator might switch to safe mode to protect sensitive electronics. An airline might reroute polar flights away from high-latitude paths where radio communication could black out. All of that preparation started because of images taken by cameras that photographed the Sun every 12 seconds. Here's the detail that puts the scale in perspective. The Solar Dynamics Observatory streams about 1.5 terabytes of data back to Earth every single day. Every day. Just from watching the Sun. That's roughly 300,000 songs downloaded every 24 hours just to monitor one star. And even with all of that data, even with thousands of images per week, even with multiple satellites watching the same event simultaneously, there was still one thing forecasters could not predict, the most important variable in the entire event. The thing that decided whether the storm would be moderate or severe. The thing that controlled whether Earth's magnetic field would open up or stay sealed. It couldn't be measured from Earth. It couldn't be predicted more than about an hour before it happened. And the solar wind was already crossing the 93 million mile gap, carrying that variable inside it, unknown until the final moment. Picture the Sun's magnetic field as a massive tangle of rubber bands stretching through its corona. In healthy regions, those bands arc up from the surface, curve through the corona, and bend back down to reconnect with the surface. They form closed loops. The plasma, the charged gas, rides along those loops and stays contained. Those closed regions are bright, dense, and relatively stable. In the coronal hole, every single one of those bands points outward, away from the Sun, into space. They form open lines that stretch for millions of miles without ever returning, and plasma riding those open lines has nowhere to go but out. The result is a fire hose. A permanent continuous stream of charged particles flowing away from the Sun along those open field lines at speeds far above the normal solar wind baseline. This is confirmed physics. The open field geometry is the direct cause of the elevated wind speed. Close the field and you trap the plasma. Open it and you release it at high velocity. Now here's where the scale gets hard to picture. The stream from this coronal hole was travelling at between 340 and 370 miles per second when it reached Earth. 370 miles per second. That's the distance from New York to Boston, travelled in less than 1 second. 16 times per second. Every second. A continuous river of charged particles moving at that speed across 93 million miles of space. And despite that velocity, it still took 2 to 3 days to arrive. The reason is the distance. 93 million miles is a number that doesn't mean much until you attach something to it. Light takes about 8 minutes to cross that gap. The solar wind from this coronal hole moving at a fraction of light speed needed 2 to 3 days. That's how empty space compresses time. But the stream doesn't arrive alone, and it doesn't arrive cleanly. In the space between the Sun and Earth, something forms ahead of every high-speed solar wind stream. The faster wind from the coronal hole slams into the slower wind that's already filling the space ahead of it. That collision creates a compressed zone of dense particles and elevated magnetic field strength. A wall of compressed solar material building up ahead of the faster stream like a snowplow pushing snow. Scientists call this a co-rotating interaction region. It forms naturally every time a high-speed stream chases a slower one through space, and this compressed wall typically hits Earth before the mainstream does. That matters because the wall carries different properties than the stream behind it. It's denser. Its magnetic field is stronger. And when it strikes Earth's protective magnetic bubble, the magnetosphere, it can trigger the first wave of geomagnetic disturbance. On May 15th, this compressed wall was projected to arrive first, hit the magnetosphere, and produce the strongest geomagnetic conditions of the entire event. The mainstream would follow, keeping conditions elevated through May 16th. 2 waves, first the wall, then the flood. But whether either wave actually caused a severe storm depended entirely on one factor, one variable embedded inside the solar wind itself, something invisible, something that couldn't be predicted from Earth until it was basically already touching the planet. And that factor has a name, a simple name, a single letter, BZ. You're swimming in it right now. The solar wind is real, it's moving, and it's passing through you at this exact moment, though you feel nothing. The solar wind is a constant flow of charged particles, mostly electrons and protons, streaming outward from the sun in every direction. It fills the entire solar system. Every planet swims in it. Every spacecraft crosses it. Every astronaut works inside it. Earth's magnetic field deflects most of it, bending the stream around the planet like water splitting around a rock in a river. Without that magnetic field, the solar wind would strip away our atmosphere the way it stripped away Mars's atmosphere billions of years ago. Mars lost its magnetic field early in its history. Its atmosphere thinned and vanished. Today, Mars's surface is exposed directly to solar wind. Earth's magnetic field is the only reason our sky is still here. That's confirmed science, and it puts this storm event in context. The solar wind that always flows past Earth moves at around 248 miles per second, fast enough to cross the continental United States in about 13 seconds. That's the baseline. That's what's always there. The stream from this coronal hole was moving at 340 to 370 miles per second, 50% faster than baseline, and speed alone doesn't determine the damage. What matters is what the wind carries inside it. The solar wind carries a magnetic field with it, woven through the stream like a current running through water. This embedded field has a direction. It points either north or south, and that direction changes the entire outcome of what happens when the wind reaches Earth. When the embedded field points north, it aligns with Earth's own magnetic field. They push against each other. The magnetosphere holds firm. The solar wind slides around the planet. Conditions stay quiet. When the embedded field points south, it's the opposite alignment. It runs anti-parallel to Earth's field. And when 2 magnetic fields are anti-parallel, something dramatic happens at the boundary. They start to connect. The field lines break apart and reconnect across the boundary, releasing energy in bursts. Solar material pours through the gaps. This process is called magnetic reconnection, and it's the mechanism behind every geomagnetic storm. During the February 2026 coronal hole event, the embedded field flipped southward and dropped to -7 nanoteslas. That number might sound small, but in terms of space weather, it was enough to unlock Earth's magnetosphere and drive a full G2 storm. Auroras appeared over Scotland. Power systems in high-latitude regions registered anomalies. Satellites adjusted their orbits, all from one variable pointing the wrong direction. For the May event, forecasters could see the compressed wall arriving. They could measure the wind speed. They could calculate the density. But the direction of that embedded field, the BZ component, couldn't be measured reliably more than about an hour before it reached Earth. The storm's true strength was unknowable until it was already hitting, and that uncertainty was sitting behind every forecast, every warning, every preparation made in the days before the weekend of May 15th and 16th. somewhere in the 93 million miles of space between the Sun and Earth, the answer was already travelling. Already locked inside the stream, just not yet revealed. The compressed wall arrived on May 15th, and what happened next depended entirely on which way that field was pointing when it got here. Forget the storm for a moment. Before any of the May events, before the coronal hole, before the warnings, the solar wind was already there, is always there. And what it does to Earth on a quiet day is already remarkable. The solar wind hits Earth's magnetosphere at a constant rate. Even on a calm day, even during solar minimum, the stream pushes against Earth's magnetic bubble from the sunlit side, compressing it into a teardrop shape. The side facing the sun is compressed inward. The side facing away is stretched into a long tail extending millions of miles behind Earth. Earth's magnetosphere extends about 40,000 miles toward the sun on the compressed side. On the tail side, it stretches over 4 million miles behind the planet. This shape isn't fixed. It flexes. It breathes. Every pulse of solar wind makes it quiver. Even in calm conditions, a small fraction of solar wind energy leaks into the magnetosphere at the poles, where the magnetic field lines dip toward Earth's surface. This drives the permanent auroral oval, a ring of glowing sky that sits above the Arctic and Antarctic at all times. On a quiet night, that oval is faint and high latitude. Most people never see it. When the solar wind speeds up, that oval expands. It moves toward lower latitudes. It gets brighter. The more energy pouring in, the farther south it slides. During the May 15th event, forecasters expected that oval to push down far enough to reach the northern United States. States like Michigan, Montana, Idaho and Washington. Northern Europe down through Scotland. That's confirmed based on the G2 storm level and the expected geomagnetic latitude of 55 degrees, where aurora visibility was projected. But here's the detail that surprises most people. Even between active events, the solar wind is doing real work on Earth systems. It continuously erodes the outer edges of the magnetosphere. It deposits energy into the upper atmosphere, driving chemical reactions in the ionosphere. It affects satellite drag in low orbit every single day. The storm event on May 15th didn't create a solar wind interaction from scratch. It amplified something that already exists and already affects Earth constantly. And here's what that means on a practical level. The infrastructure humans depend on, the power grids, the GPS satellites, the radio systems, those systems were engineered with the baseline solar wind in mind. Engineers know the constant pressure is there. They build around it. What engineers cannot fully protect against is a sudden, sustained increase. A surge that pushes systems beyond their normal operating range. The same way a house built to handle regular rain isn't necessarily ready for a flash flood. The May event was a flash flood. The baseline solar wind is the constant rain. Both are real, both are always there, only one makes the news. And the surge headed toward Earth on May 15th was carrying something that even the most advanced monitoring equipment couldn't measure in advance. Every system waiting for the storm, every satellite on alert, every grid operator watching the monitors, all of them waiting for one variable to reveal itself. The direction of a magnetic field. Invisible, embedded in a stream of particles crossing 93 million miles. And once it arrived and turned the wrong way, everything would change very fast. Speed matters in space weather. But the numbers mean nothing without context. The baseline solar wind, the constant river of particles always flowing past Earth, travels at around 248 miles per second. That sounds fast. It's incredibly fast by any human standard. A commercial aeroplane flies at about 500 miles per hour. The solar wind moves at about 900,000 miles per hour. You could fly from New York to Los Angeles in about 13 seconds at that speed. And that's the quiet version. That's the calm baseline. The stream from the May coronal hole was clocked at between 340 and 370 miles per second by May 15th. That's around 1.33 million miles per hour, roughly 50% faster than the baseline that's always there. For comparison, NASA's fastest spacecraft ever built, the Parker Solar Probe at its closest pass to the Sun, reaches speeds of around 430 miles per second. The solar wind from this coronal hole was moving at roughly 85% of that speed on its own, with no engine, no rocket, just open magnetic field lines releasing plasma into space. That speed difference is what drives the storm. When fast wind slams into the slower wind already filling space, it compresses it. The compressed zone builds up ahead of the fast stream, and that's the co-rotating interaction region discussed earlier. But the speed itself also matters once the stream reaches Earth's magnetosphere, because faster wind carries more kinetic energy per particle. More energy hitting the magnetic bubble means more pressure. More pressure means more deformation of the magnetosphere. More deformation means more opportunities for magnetic reconnection on the sunward side. The Space Weather Prediction Center confirmed the wind speed measurement of 550 to 600 kilometers per second on May 15th. That translates to 340 to 370 miles per second. The measurement came from real-time solar wind monitors, satellites positioned about 1 million miles sunward of Earth, sitting at a gravitational balance point called the L1 Lagrange point. Those satellites gave forecasters about an hour of advance warning when the wind actually arrived, 1 hour between detection and impact. But the speed measurement alone, even though it was elevated and confirmed, still didn't settle the storm's severity. Because speed is only half of what drives a geomagnetic storm. The other half is that magnetic field direction, the BZ component, which couldn't be confirmed until the wind was essentially already at Earth's doorstep. For a comparable April 2026 event, a large equatorial coronal hole drove solar wind speeds as high as 435 miles per second. That event was studied as a benchmark. The May coronal hole was producing speeds in the same ballpark, and in events like these, something else was also happening. A separate region of the Sun entirely, a sunspot called AR4436, was building pressure behind the scenes. It had nothing to do with the coronal hole, except that it shared the same sun, and its behaviour was making space weather scientists very nervous. Because AR4436 had already fired 5 major eruptions that no one on Earth had even seen. Think of the coronal hole's solar wind stream as a freight train. The train is fast, it's heavy, it's heading toward Earth at over 1 million miles per hour. But ahead of the train, pushing through the slower air in front of it, is a pressure wave. A wall of compressed air that arrives a fraction of a second before the train itself. Anyone standing close enough feels that pressure wave before they hear the train. In space, the same physics plays out over millions of miles instead of feet. When the fast solar wind from the coronal hole chases the slower background wind already filling the space between the Sun and Earth, it plows into it. That collision point builds up into a compressed zone of dense particles and elevated magnetic field strength. Scientists call it a co-rotating interaction region. It forms because the two wind streams rotate with the Sun, and where the fast stream catches the slow stream, a boundary piles up. This compressed region travelled ahead of the main high-speed stream the entire way from the Sun to Earth. On May 15th, forecasters expected the compressed wall to arrive first, and that arrival was projected to produce the strongest geomagnetic conditions of the entire event, even before the main stream reached Earth. The wall carried denser particles and a stronger magnetic field than the stream behind it. When it hit Earth's magnetosphere, it was expected to trigger the initial surge to G2 conditions. A KP index of 5.67 was the peak forecast, putting the event solidly in the moderate storm category. The KP index, introduced in 1949 by German scientist Julius Bartels, runs from 0 to 9. 0 means perfectly quiet. 9 means extreme, civilization scale threat. A 5 means a G1 minor storm. A 6 means G2 moderate, and 9 means G5, the level that knocked out power across Quebec in 1989 for 9 hours and left 6 million people in the dark. The May forecast of 5.67 sat right at the G2 line. Elevated, disruptive, but contained as long as the magnetic field direction cooperated. After the compressed wall passed, the actual high-speed stream from the coronal hole would arrive. Wind speed would climb, density would drop, temperatures in the solar wind would rise. This second phase was expected to keep geomagnetic conditions elevated at G1 levels through May 16th, before gradually fading. 2 distinct phases. First the wall, then the flood. Each with different characteristics, each capable of triggering different kinds of disruption on Earth. For the technology systems that depend on a stable space environment, 2 days of elevated conditions meant 2 days of vulnerability. Power grids watching for induced currents, satellites running orbit corrections, pilots on polar routes monitoring radio silence zones. And somewhere behind all of that, one factor still unresolved, still hidden inside the incoming stream, still unknowable until the moment of arrival, the magnetic field direction, the single variable that controlled everything. And while Earth braced for the wall to hit, something else was happening on the Sun itself, something that had nothing to do with the coronal hole, but everything to do with what might come next. A sunspot was rotating into view, and it had a history. In 1949, a German scientist named Julius Bartels had a problem. Geomagnetic disturbances, disruptions to Earth's magnetic field caused by solar activity, had been recorded for over a century. Scientists had detailed logs, but those logs were messy. Different observatories used different scales, different countries reported in different formats. There was no universal language for how disturbed the magnetic field actually was at any given moment. Bartels fixed that with a single number. He developed the KP index, a planetary scale measurement of geomagnetic disturbance averaged from magnetometer stations spread across Earth. The index runs from 0 to 9, with each full number divided into thirds for finer resolution. 0 is perfectly quiet, 3 is unsettled, 5 is the beginning of a storm, 9 is the worst Earth has ever recorded. Every 3 hours a new KP value is calculated, day and night, continuously, since 1949. For the May 15th event, forecasters projected a peak KPP of 5.67. That put the event solidly in G2 territory, which is the moderate storm category on the National Oceanic and Atmospheric Administration's 5-level scale. Here's what each level actually means in practical terms. G1 KP of 5 is minor. Power systems experience small fluctuations. Some satellite orientation systems need adjustment. Aurora becomes visible down to around geomagnetic latitude 65 degrees, roughly the latitude of Fairbanks, Alaska. G2 KP of 6 is moderate. High latitude power systems may see voltage alarms. Satellite drag increases noticeably. Aurora pushes down to around 55 degrees latitude, reaching northern Scotland, southern Scandinavia, and the northern edge of the continental United States. G3 KP of 7 is strong. Widespread voltage corrections on power grids. Low-frequency radio navigation signals become unreliable. Aurora visible as far south as Illinois or Oregon. G4 KP of 8 is severe. Possible widespread voltage control problems. Some protective systems may trip, removing assets from grids. Aurora visible as far south as Alabama or Northern California. G5, KP of 9, is extreme. Complete collapse of high-frequency radio communication on the sunlit side of Earth. Possible widespread grid failures. Satellite operations severely disrupted. Aurora visible near the equator. The Quebec event in 1989 was a G5. 9 hours of darkness for 6 million people in Canada. The May event was forecast at G2, disruptive, confirmed, but far from catastrophic, assuming the embedded magnetic field in the solar wind stayed cooperative. And that assumption was the entire gamble. Because the KP index tells you how disturbed the field already is, it measures what happened. The embedded BIS field decides what's about to happen. And BIS was still unknown. The storm was arriving, the wall of compressed solar wind was hitting Earth's magnetosphere, and the next few hours would reveal whether the magnetic field direction opened Earth's defences or kept them sealed. But even as all of this unfolded, there was a second threat developing on the Sun that had nothing to do with the coronal hole at all. The scale exists because not all storms are equal. A thunderstorm that knocks out your power for an hour is different from a hurricane that flattens a city. Both are weather events, both count as storms, but treating them as equivalent would be a mistake. The same logic applies in space. The National Oceanic and Atmospheric Administration built a 5-level scale specifically to separate minor disruptions from civilization-scale threats. Each level has a name, a number, and a list of real-world consequences that get progressively harder to recover from. G1 is minor. The lowest level, it still triggers effects. High-latitude power systems see minor fluctuations. Satellites need small orbit adjustments. Migratory animals that use Earth's magnetic field for navigation, birds, whales, certain fish, can show behavioural disruption. Aurora becomes visible at high latitudes. G2 is moderate. The level forecast for May 15th. Voltage alarms start appearing in high-latitude power systems. Satellite drag increases because the upper atmosphere expands during storms, creating more friction for low-orbit spacecraft. Some high-frequency radio communication at polar routes becomes unreliable. Aurora visibility extends to around geomagnetic latitude 55 degrees, which means northern Scotland, Scandinavia, Iceland, and the northern United States tier. G3 is strong. Voltage corrections become widespread on power grids. Operators must actively intervene to prevent equipment damage. Low-frequency navigation signals used by ships and submarines become degraded. Surface charging on satellites increases. Aurora visible down to Illinois and Oregon. G4 is severe. Now the grid is in real danger. Widespread voltage control problems can cause protective relays to trip, cutting sections of the grid offline to prevent damage from spreading. Satellite navigation systems experience significant errors. Some satellites may need to be powered down to protect electronics. Aurora visible near the Gulf of Mexico. G5 is extreme, the top of the scale. At G5, high-frequency radio communication on the entire sunlit side of Earth goes dark. Pipeline operators see dangerous induced currents running through metal. Transformers can overheat and fail. Once a large transformer fails, replacing it takes months because there are only a handful of manufacturers worldwide and each unit is custom built. Aurora visible near the equator. The 1989 G5 event knocked out the entire Quebec power grid in 90 seconds. 6 million people lost power. The blackout lasted 9 hours. Transformers in New Jersey and the United Kingdom also failed. The total cost ran into the billions. For May 15th, 2026, the confirmed forecast was G2, not G5. The gap between those two levels is enormous in terms of real-world impact. But the gap between G2 and G3 depends on one thing. The same thing it always comes back to, whether the embedded magnetic field in the arriving solar wind turns south, whether BZ flips. If BZ flipped and stayed negative long enough, a G2 forecast could become a G3 event within hours. That uncertainty was real, confirmed by forecasters, built into every warning issued. And even as the scale was being discussed, even as grid operators and satellite teams were running through their protocols, a completely separate event was building on the other side of the sun. An event that had already fired 5 times, with no one watching. Here's the most unsettling fact about space weather forecasting. Scientists can track the coronal hole from the moment it forms. They can measure the wind speed as it approaches Earth. They can calculate the density of the incoming stream. They can model the arrival time to within a few hours. They can predict the storm category with reasonable confidence days in advance. But the one variable that decides the storm's actual severity, the one number that controls whether Earth's magnetic field holds firm or splits open, can't be measured reliably until the solar wind is basically already touching the planet. That variable is the north-south orientation of the magnetic field embedded in the solar wind. Scientists call it BZ. When BZ points north, it aligns with Earth's field. Pressure builds, but the magnetosphere stays sealed. When BZ points south, it opposes Earth's field. The two fields interact at the boundary, snap apart and reconnect in ways that funnel solar energy deep inside. Forecasters call the southward turn of Bez the most important and least predictable event in space weather. The reason they can't predict it further in advance is distance. The solar wind carries the BZ information inside it as it travels 93 million miles from the Sun. The only measurement point that can detect BZ before it hits Earth sits about 1 million miles sunward of the planet, at a gravitational balance point where solar wind satellites orbit. That buoy in space gives forecasters around 60 minutes of warning. 1 hour. That's the full advance notice for the most important variable in the storm. During the February 17, 2026 coronal hole event, which was the last comparable storm before May, BZ repeatedly dipped to -7 nanoteslas in the southward direction. That flip drove sustained G2 conditions. Power systems registered anomalies. Auroras lit up Scotland and Scandinavia. The BZ flip was the trigger. For the May 15th event, as the compressed wall of solar material approached Earth's magnetosphere, forecasters were watching BZ in real time, not predicting it, watching it, waiting for it to make its move. If BZ stayed north, the storm remained moderate. A G2 event with elevated aurora, some satellite adjustments, manageable grid effects. If BZ turned south and stayed there, conditions could escalate toward G3. Voltage corrections across high-latitude grids, more significant satellite drag, radio communication trouble on polar flight paths, and if BZ swung deeply south and held, the upper end of the storm range opened up. This is a confirmed limitation of current space weather science. Not a gap in forecasting skill, but a physical boundary on how far in advance the magnetic field direction can be known. The information simply doesn't exist until the wind carries it close enough to measure. Every grid operator, every satellite team, every Aurora enthusiast waiting in a field in northern Scotland on the night of May 15th was living inside that uncertainty. The wall was hitting. The answer was arriving. And the next development on the Sun itself was almost as alarming. Because while everyone watched Biz, a sunspot was finishing its rotation into Earth's direct line of sight. With a confirmed history of major eruptions that no one had seen coming. Magnetic reconnection sounds like a textbook term. It's actually one of the most violent processes in the solar system. Here's what happens. Earth's magnetic field extends outward from the planet in a protective shell. On the sunward side, it curves around and deflects the solar wind. The boundary between Earth's field and the solar wind's field is called the magnetopause. Normally, these two fields press against each other without merging. The solar wind slides around the planet. Earth stays protected. But when the solar wind's embedded magnetic field points south and Earth's equatorial field points north, something changes at that boundary. The two fields are now oriented in opposite directions. Antiparallel. And antiparallel magnetic field lines carry enormous tension between them. At the point where they press together, the opposite fields can break. They snap apart and reconnect across the boundary, joining solar field lines to Earth's field lines. This reconnection releases energy explosively. Plasma from the solar wind pours through the breakpoint, accelerating inward along the newly connected field lines. Think of it like this. Two magnets pressed together with opposing poles repel. Push them hard enough together and something gives. In this case, what gives is the boundary itself. The field lines tear and fuse with each other. The energy released by one reconnection event can be equivalent to tens of millions of atomic bombs released over the course of a geomagnetic storm. That energy doesn't all arrive at Earth's surface, thankfully. It gets distributed through the magnetosphere, accelerating particles along field lines toward the poles. Those accelerated particles are what create auroras. When they slam into oxygen and nitrogen molecules in the upper atmosphere, they excite those molecules and cause them to release light. Different molecules, different altitudes, different colours. The reconnection process drives all of it. During the February 2026 coronal hole event, BZ dropped to -7 nanoteslas and sustained that direction long enough to drive repeated reconnection events. The result was a G2 storm with visible auroras over Scotland and Scandinavia. The mechanism was this: field lines snapping, energy pouring through, particles racing toward the poles. For the May event, every forecaster watching the BZ readings was watching for exactly this sequence to begin or stay quiet. The moment Bs turned south, reconnection would start. The moment reconnection started, the storm level would start climbing. The measurement satellites at the 1 million mile marker were sending data in real time. Wind speed, particle density, magnetic field orientation, all flowing back to Earth continuously. And the reading that mattered most was updating every few seconds. The compressed wall had arrived. The magnetosphere was under pressure. The Aurora oval was already brightening at high latitudes. Now the question was how far it would go. And here's what makes the answer genuinely surprising. Even a G2 storm, the one that was forecast, carries enough energy to start disrupting the systems modern life depends on in ways most people never think about. Power grids, GPS radio communications, satellites, all of them exposed, all of them vulnerable in different ways, and the damage mechanism for each one is completely different. In 1989, the lights went out across Quebec. The event lasted 9 hours. 6 million people sat in the dark. Transformers failed across Canada and the United States. The cause was a G5 geomagnetic storm. The mechanism was something most people have never heard of: geomagnetically induced currents. Here's how it works. When Earth's magnetic field fluctuates during a geomagnetic storm, it does something unexpected. It creates electrical currents in the ground itself, not in the air, in the actual earth beneath your feet. Those currents follow conductive paths, and long metal conductors are excellent paths. Power lines, pipelines, railway tracks, and submarine cables all become channels for these induced currents. In a power grid, the problem is specific. Power lines are designed to carry alternating current, electricity that switches direction 60 times per second in the United States. geomagnetically induced currents flow in the same direction continuously. They don't alternate. They sit on top of the normal current and push transformers into a condition called magnetic saturation. A saturated transformer can't regulate voltage properly. It overheats. In a short storm, this causes voltage alarms and efficiency losses. In a sustained storm, the heat builds until the transformer fails permanently. Replacing a large high-voltage transformer takes months. They're custom-built, measured in hundreds of tons, and there are only a handful of factories worldwide that make them. During the 1989 event, several transformers in New Jersey and the United Kingdom failed within hours. The Quebec grid collapsed in 90 seconds. At G2 level, the May event was not expected to cause transformer failures in most systems. Voltage alarms in high-latitude regions? Yes. Active monitoring and load adjustments by grid operators? Yes. Potential disruption to parts of the grid serving northern Canada and Scandinavia? Yes. But G2 is the level where the risk becomes real enough to act on. Grid operators in affected regions don't wait to see what happens. They start load management. They reduce the load on transformers in vulnerable areas. They monitor for anomalies every few minutes. The threat is confirmed. The physics is understood. The 1989 event proved what the worst case looks like. And the uncomfortable truth is that the power grid today, while better monitored than in 1989, is also larger and more interconnected. A failure in one node can cascade through a wider system faster than before. Grid engineers know this. Space weather forecasters know this. The gap between knowing and fully solving it is still open. But the power grid is only one vulnerable system. While grid operators watched their monitors on May 15th, another network was quietly experiencing its own kind of disruption. A network most people touch dozens of times a day without thinking about it. Every time you use GPS, you're trusting a signal that travels from space through Earth's upper atmosphere to your device. That journey normally takes about 67 thousandths of a second. The signal travels at the speed of light from a satellite about 12,500 miles above Earth. Your phone measures how long the signal takes to arrive, compares it to signals from 3 or 4 other satellites simultaneously, and calculates your position to within a few feet. That calculation depends on one assumption: that the signal travels through the atmosphere at a predictable, uniform rate. Geomagnetic storms break that assumption. The ionosphere is a layer of Earth's upper atmosphere sitting between about 37 and 600 miles above the surface. It's filled with charged particles created by solar radiation constantly hitting the upper air. Normally it's structured and predictable. Signals from GPS satellites pass through it in ways that GPS receivers are calibrated to expect. During a geomagnetic storm, the ionosphere becomes turbulent. The same energy that drives auroras also energizes and restructures the ionosphere in irregular ways. Patches of higher and lower electron density form unpredictably. When a GPS signal passes through those patches, it bends. It slows in some places and speeds up in others. It scatters. The receiver on the ground sees a signal that's arrived slightly late or from a slightly wrong angle. It calculates a position. That position is wrong. The error during a G2 storm can reach several meters for standard consumer GPS. For precision GPS systems used in aircraft navigation, surveying and precision agriculture, the error can be larger and harder to correct for. Aviation is particularly affected. Planes flying polar routes, the shortest path between North America and Asia, fly directly through the auroral zone during high geomagnetic activity. At G2, high-frequency radio communication on those routes becomes unreliable. Airlines sometimes reroute polar flights away from high latitudes specifically during geomagnetic storms, adding flight time and fuel cost. Emergency services using high-frequency radio for coordination, maritime operators, and military communication systems all face similar disruptions. And while GPS errors measure in meters, the economic cost of those errors in delayed flights, rerouted ships, and disrupted construction projects adds up to billions of dollars globally during major storm events. For the May 15th event, G2 conditions meant elevated ionospheric disruption over the regions most directly affected by the Aurora, exactly the same high-latitude regions where polar flights operate. The disruption was confirmed as a projected effect. The precise scale depended on BES behaviour after the compressed wall arrived. And while GPS signals bent through a disturbed ionosphere, something else was happening at much lower altitudes. Something that affected satellites operating closer to Earth's surface. Those satellites were falling. Satellites in low orbit are falling constantly. That's how orbital mechanics works. A satellite doesn't float freely. It's in a constant state of controlled falling, moving forward fast enough that the curve of Earth drops away beneath it at the same rate it falls toward the planet. The result is a stable orbit. But orbit isn't perfectly stable. There's always a trace amount of atmosphere even at orbital altitudes. At around 250 miles above Earth, the altitude where the International Space Station orbits, the air is 1 trillion times thinner than at sea level. Still, it's there. And it creates drag. That drag slowly pulls satellites lower over time. Without periodic boosts, they'd eventually spiral back into the atmosphere and burn up. Geomagnetic storms change the drag equation. When solar wind energy pours into the magnetosphere during a storm, it heats the upper atmosphere. The particles at that altitude gain energy and move faster. The atmosphere expands upward, pushing the boundary of measurable air density higher into space. A satellite that was orbiting in near vacuum suddenly finds itself in slightly denser air. The drag increases. The orbit decays faster. During the May event, the thousands of satellites in the Starlink constellation, orbiting at altitudes between 220 and 340 miles, were directly in the zone affected by atmospheric expansion during a G2 storm. Each satellite requires continuous orbit corrections to maintain altitude. During storms, those corrections become more frequent and consume more fuel. During the major geomagnetic storm of May 2023, which reached G5 levels, SpaceX reported that some Starlink satellites were losing altitude faster than their thrusters could compensate. Some earlier incidents involved satellites being lost entirely after a storm pushed them into orbital decay before operators could respond. The May 2026 event was forecast at G2, less severe. But with hundreds of satellites in low orbit operated by dozens of companies, even small increases in drag across the entire constellation add up to significant fuel expenditure and operational overhead. And there's a separate effect for satellites with exposed electronics. Geomagnetic storms accelerate the buildup of static charge on satellite surfaces, a phenomenon called surface charging. In severe cases, that charge can discharge suddenly, damaging sensitive electronic components. At G2 levels, this risk is elevated but manageable with careful monitoring. Grid engineers on the ground watched for induced currents. GPS receivers bent their signals. Satellites adjusted their orbits. And pilots on polar routes faced a fourth kind of disruption entirely, one that's been a concern since the early days of aviation. The radio silence that falls over the poles during geomagnetic storms. Long before GPS, pilots crossed oceans using radio. High-frequency radio, or HF radio as it's commonly called, works by bouncing signals off the ionosphere. A transmitter on the ground sends a signal upward at an angle. The ionosphere reflects it back down thousands of miles away, Another bounce, another reflection, and the signal can travel halfway around the world using the sky as a mirror. Aviation still depends on this system, especially over the oceans and the poles, where satellite communication coverage has traditionally been limited. Ships use it. Emergency services in remote areas use it. Military operations use it. During a geomagnetic storm, the ionosphere stops being a mirror. The turbulence and irregularity that disrupts GPS signals does something more severe to high-frequency radio. Instead of reflecting the signal, the disturbed ionosphere absorbs it. The signal goes in and doesn't come back out. From the perspective of anyone trying to communicate, the frequency simply goes dead. The effect is strongest at high latitudes, directly beneath the auroral zone, and it can spread to lower latitudes during severe storms. During a G2 event, high-latitude radio blackouts are a confirmed effect. Confirmed by decades of observations, airlines flying polar routes between North America and Asia or Europe actively monitor geomagnetic conditions and work with air traffic control to shift frequencies or alter routes when conditions deteriorate. During the May 15th event, the zones at greatest risk were exactly the regions where the Aurora oval was pushing down: northern Canada, Iceland, Greenland, Norway, Sweden, and northern Scotland. Pilots crossing those regions on that night faced elevated risk of partial or complete high-frequency radio loss. The solution is to drop to lower frequencies, shift to satellite communication where available, or reroute to avoid the most affected areas. Each option adds cost and complexity. For a single flight, it's manageable. Across hundreds of flights simultaneously during an active storm, the coordination required becomes significant. And all of this disruption, the grid effects, the GPS bending, the satellite drag, the radio blackouts, these are the consequences of the storm reaching Earth. The storm itself is ultimately driven by particles colliding with Earth's atmosphere, and those collisions produce something that billions of people have looked up at for all of human history: the Aurora Borealis. The northern lights, visible during this storm, farther south than most people had ever seen them. And the science behind why they glow the colours they do is one of the most specific and surprising stories in all of atmospheric physics. Auroras have a reputation for being mysterious. Glowing curtains, dancing lights. Ancient cultures thought they were spirits, fires, reflections of armies fighting in the heavens. The actual science is more specific, and in some ways, more astonishing. Every aurora starts with the same sequence. Solar wind particles, electrons and protons funnel along Earth's magnetic field lines toward the poles. They accelerate as they go. By the time they reach the upper atmosphere, they're moving fast enough to collide violently with the gas molecules there. The atmosphere at aurora altitude sits between about 50 and 186 miles above Earth's surface. That's high above the weather, high above where planes fly, but still within Earth's protective gas layer. At those altitudes, the air is mostly oxygen and nitrogen, thinly spread but present. When a fast solar particle slams into an oxygen or nitrogen atom, it knocks one of that atom's electrons up to a higher energy level. The atom is now in an excited state. It can't stay there. Within a tiny fraction of a second, the electron drops back down to its normal position, releasing the extra energy as a photon of light. The colour of that photon is determined by which atom produced it, and at what altitude. Green auroras come from oxygen atoms at altitudes between 62 and 124 miles. This is the most common aurora colour, and it's what most people picture when they imagine the northern lights. Oxygen at that altitude releases green light most efficiently when excited. Red auroras come from oxygen too, but at higher altitudes. Above 124 miles, oxygen atoms are more spread out. They get excited but take longer to release their photon, because the collisions that would knock them back down are less frequent. This longer wait produces red light instead of green. Blue and purple auroras come from nitrogen molecules lower in the atmosphere. Nitrogen releases a range of colours in the blue-purple spectrum when excited by solar particles. During a G2 storm, all three types can appear simultaneously, stacked by altitude. A display might show a green base, a red top, and blue-purple fringes, all produced by different atoms at different heights, all caused by the same stream of particles funneling down the same magnetic field lines. The May 15th event pushed the auroral oval down to geomagnetic latitude 55 degrees. That put the display within reach of northern Scotland, Scandinavia, Iceland, and the northern tier of the United States. States like Michigan, Montana, Minnesota, and Washington had confirmed viewing windows. One detail that surprises people every time. Smartphone cameras detect auroras better than the human eye during moderate storms. Camera sensors are sensitive to wavelengths at the edges of visible light that human eyes don't register well in low light conditions. People standing outside on May 15th who saw nothing with their eyes sometimes held up their phones and captured clear green bands across the sky. The particles causing that light show were the same ones that bent GPS signals, disrupted HOPE radio, increased satellite drag, and induced currents in power lines. All of it connected, all of it from the same source. And while Earth's systems absorbed the impact of the coronal hole stream, a separate and arguably more dangerous situation was developing on the Sun itself. A sunspot had finished rotating into full Earth-facing position, and its history was the kind that makes space weather scientists lose sleep. Most people think auroras are just green. That's the one in every photo, the one on every travel poster for Iceland and Norway. But during a strong geomagnetic storm, the sky runs through an entire spectrum. Green at the base, red bleeding upward, blue and purple flickering at the edges. Each colour is a separate story happening at a separate altitude, driven by a separate chemical reaction. Start with green. Oxygen atoms sitting between 62 and 124 miles above Earth's surface get struck by incoming solar particles. The collision knocks an electron inside the oxygen atom to a higher energy level. The atom holds that energy for a fraction of a second, then releases it as a photon. At that altitude and pressure, the photon comes out green. This reaction happens millions of times per second, across hundreds of miles of sky during an active storm. Now go higher. Above 124 miles, oxygen atoms are still there, but the air is thinner. Collisions between atoms are less frequent. When a solar particle excites an oxygen atom at this altitude, the atom has to wait longer before another collision knocks it back down. That longer wait changes the physics. The atom releases its energy differently. The photon comes out red. Red auroras are rarer because this process requires a specific altitude and a specific level of geomagnetic activity. They appear above the green layer, often as a deep crimson ceiling sitting over the brighter green base. During the most intense parts of a G2 or G3 storm, both layers can be visible simultaneously, stacked like colours in a sunset that's happening directly overhead. Then there's the blue and purple fringe. That comes from nitrogen, which behaves differently from oxygen. Nitrogen molecules in the lower part of the auroral zone, between about 50 and 62 miles altitude, release light in the blue-violet range when excited. These colours often appear at the edges of auroral curtains, where the particle beam is widest and reaches deepest into the atmosphere. During the May 15th event, all three colour sources were active. The compressed wall drove particle injection into the magnetosphere. those particles funneled along field lines toward both poles. Over northern Scotland, Scandinavia and northern Canada, observers and cameras recorded the display as it built through the evening hours. Here's the detail that changes how people think about this. The light from an aurora travels around 8 minutes to reach the sun from Earth. The particles causing the aurora left the sun 2 to 3 days earlier. The light you see when you look at an aurora was born in a chain of events that started on a star 93 million miles away, days before. You're watching chemistry that started on the sun, and some people on May 15th were watching it on their phones. Camera sensors pick up green and purple wavelengths that human eyes struggle to detect in low-light conditions. People standing in dark fields in Montana or Minnesota held up their phones and saw active aurora bands their own eyes registered only as a faint glow or nothing at all. But the aurora is only the visible surface of a storm that runs much deeper. The same particles lighting up the sky were doing something else entirely on the ground level. Something that had been building on the sun's surface for days, completely separate from the coronal hole, was about to enter the picture. And it had a history that started on the side of the sun Earth never sees. For most of human history, the aurora was a mystery. Ancient Norse people called it the Bifrost, a burning bridge between Earth and the realm of the gods. Indigenous communities across the Arctic interpreted the lights as ancestors dancing or as spirits playing games in the sky. Medieval Europeans sometimes panicked, believing the red aurora was a sign of coming war or plague. They weren't wrong that something powerful was happening, they were just missing the mechanism. Now the mechanism is so well understood that a 15-year-old with a smartphone can detect an aurora the naked eye cannot see. Here's why that works. Human eyes evolve for daylight. The cells in your retina that handle colour vision, called cone cells, need a certain amount of light to activate properly. In low light conditions, your eyes switch to rod cells, which are more sensitive but can't process colour well. That's why everything looks greyish in dim light. Camera sensors don't have this limitation. A modern smartphone sensor collects light by exposing millions of tiny photosensitive pixels for a set duration. Even a half-second exposure accumulates enough photons from a faint aurora to register green or purple clearly in the image. The sensor sees what your eye cannot. During mild to moderate auroras, like the kind produced by a G2 storm at the edge of visibility latitude, the display can be completely invisible to a naked eye observer, while showing up bright and green on a phone camera pointed at the same sky. This was confirmed repeatedly during the February 2026 coronal hole event. Observers in northern England, southern Scotland and the northern United States reported seeing nothing overhead, then checking their cameras and finding vivid aurora bands already active. The storm was there, their eyes just weren't built to catch it. For May 15th, the Space Weather Prediction Centre and the UK Meteorological Office both issued aurora alerts with specific guidance. Dark sky, away from city lights, phone camera aimed north, exposure set manually if possible. The advice was precise because the science is precise. And the aurora wasn't just a visual event, it was a marker. Every photon lighting up a camera sensor overhead represented a stream of particles that had also hit GPS satellites, bent radio signals, increased drag on spacecraft, and pushed currents through power lines. The beauty and the disruption share the same cause. But even as aurora watchers positioned themselves across Scotland and Montana on the night of May 15th, another chapter of this story was developing on the sun itself. One that had been quietly building since before the coronal hole was even detected. A sunspot had been firing eruptions for days on the far side of the sun, out of sight, and now it had rotated into view. The question was whether it was finished erupting or just getting started. Aurora forecasting used to be guesswork. Scientists knew the sun drove the displays. they knew higher geomagnetic activity pushed the aurora to lower latitudes. But predicting exactly where a person could step outside and look up on a specific night from a specific city was more art than science. Today, the National Oceanic and Atmospheric Administration publishes real-time auroral oval maps. The oval is a ring of activity that circles each magnetic pole. During quiet conditions, it sits tight around the Arctic, visible only from Iceland, northern Scandinavia, and the far northern reaches of Canada and Alaska. As geomagnetic activity rises, it expands like a ripple moving outward from a dropped stone. For a G2 storm, the oval expands to roughly geomagnetic latitude 55 degrees. That line crosses northern Scotland, southern Scandinavia, Iceland, the southern tip of Greenland, and, in North America, a band running through the northern United states of Michigan, Minnesota, Montana, Idaho, and Washington. On the evening of May 15, 2026, that expansion was confirmed. The UK Meteorological Office issued a direct aurora forecast for northern Scotland during the UTC night hours. Observers in the Highlands and Orkney reported clear skies and active displays. In North America, aurora alerts went out across the northern tier states. The National Weather Service issued viewing guidance. Dark sky sites filled up. People drove out of cities into rural areas specifically to watch. And in the southern hemisphere, the same storm drove a southern lights display, called Aurora Australis, visible from the far south of New Zealand during the May 16th and 17th window as the high-speed stream continued past Earth. The displays appear at both poles simultaneously. When particles funnel down field lines toward the Arctic, the same process happens at the Antarctic end of those same field lines. Every Northern Lights event has a mirror image in the south. For the G2 event, the southern display was expected to reach parts of the South Island of New Zealand, southern Australia's island state of Tasmania, and the southern tip of South America. Two hemispheres, same storm, same particles, same physics. But here's what makes this display different from every aurora humans watched for thousands of years. Those observers had no warning. They stepped outside and the sky was green or red, or the aurora wasn't there at all. Now, the Space Weather Prediction Center updated its auroral oval maps every 10 minutes with real-time data. Observers could watch the oval expand on their phones in real time, check local cloud cover forecasts, and position themselves in the optimal viewing location before the display peaked. The storm that ancient Norse people called Bifrost was fully mapped, forecast and streamed live in 2026. But the storm causing it had a second chapter, one driven by a completely different region of the Sun, and that region had already been active for days, firing eruptions Earth never saw coming. On Mother's Day, May 10th, 2026, at exactly 13:39 Coordinated Universal Time, a sunspot called AR 4436 erupted. The flare it produced was classified M5.7, which sits in the middle of the solar flare scale, powerful enough to cause radio blackouts, powerful enough to launch a coronal mass ejection, a billion-ton cloud of magnetized plasma, into space at around 400 miles per second. Space weather agencies track the ejection carefully. Models from the Solar and Heliospheric Observatory showed the bulk of the cloud would fly east of Earth. A near miss. A glancing blow at most, expected to brush Earth's magnetosphere lightly around May 13th with minimal effect. What concerned scientists more than the flare itself was the sunspot's history. AR 4436 had been active for days before that Mother's Day eruption. But during those days, it was on the far side of the Sun, the hemisphere permanently facing away from Earth. From Earth's perspective, the Sun's far side is completely invisible. No direct observation is possible. Scientists confirm that AR 4436 fired at least 5 significant coronal mass ejections while on the far side before it ever rotated into view. 5 eruptions. Unseen. Untracked in real time. Gone into deep space with no Earth impact, but demonstrating a level of magnetic instability that made forecasters nervous. When a sunspot is that active on the far side, it doesn't calm down just because it rotated into view. By mid-May, AR4436 was finishing its rotation toward the Earth-facing hemisphere. The same rotation that brought the coronal hole into view was also bringing this sunspot into direct alignment. The concern was straightforward. A sunspot that fires 5 times while out of sight might fire again now that it's pointed directly at Earth. And a coronal mass ejection aimed directly at Earth is a fundamentally different threat than a coronal hole windstream. The coronal hole produces a sustained elevated wind that takes 2 to 3 days to arrive and drives G1 to G2 conditions. A coronal mass ejection is a concentrated blast. It can travel faster, carry a stronger magnetic field, and if the embedded BZ flips deeply south during impact, it can drive storms into G3, G4, or at the extreme end, G5 territory. The M5.7 flare on May 10th was serious. The near-miss trajectory meant Earth avoided the worst of it. But with AR4436 now rotating into full Earth-facing position, space weather agencies confirmed it as a top priority watch region. The next eruption might land differently. And while forecasters watched AR4436, a question that seemed separate was actually connected to both the sunspot and the coronal hole. A question about where the solar cycle stood in 2026 and what that meant for the months ahead. 5 eruptions, no one watching. That's the situation with AR4436 in the days before May 10th. It was sitting on the sun's far side, invisible from Earth, firing coronal mass ejections into space. Each eruption confirmed the region was magnetically unstable, loaded with energy, and capable of major events. The challenge of far-side solar activity is real and confirmed. Earth-based solar observatories can only watch the hemisphere facing us. NASA and international agencies have worked to address this with missions like the Solar and Heliospheric Observatory and the Twin Solar Terrestrial Relations Observatory spacecraft, which positioned sensors to observe the Sun from different angles. But full, continuous coverage of the far side in high resolution remains limited. What scientists can do is track a sunspot's behaviour before it rotates out of view, then make informed assumptions about its state when it rotates back in. A sunspot that was producing multiple eruptions before disappearing around the limb of the Sun carries that history with it. AR4436 arrived on the Earth-facing side of the Sun with a violent record already attached. The M5.7 flare it fired on May 10th generated a giant cavity in the Sun's corona, visible in NASA's Solar Dynamics Observatory imagery in extreme ultraviolet. The ejection it launched moved at approximately 400 miles per second, slower than the solar wind from the coronal hole, but carrying a concentrated magnetic punch. The trajectory models were the relief. The bulk of the ejection passed east of Earth. A glancing interaction around May 13th produced minor effects. The main blast missed. But here is what space weather agencies confirmed in public statements around May 11th and 12th. AR4436 was still active, still rotating into a more directly Earth-facing position. A next eruption from the same region, if stronger and aimed slightly differently, would have a substantially higher chance of direct impact. An X-class flare, the highest category, from a region pointed directly at Earth can drive a G3 to G5 storm depending on the ejection speed and magnetic field properties. AR4436 had the magnetic complexity that produces X-class events. Forecasters explicitly described it as a region being watched very closely. The language used in public space weather briefings was careful, but the implication was clear. This region was not done. So during the weekend of May 15th and 16th, Earth was simultaneously absorbing the high-speed stream from the coronal hole and watching AR4436 with the expectation that another, potentially larger event could follow within days. 2 separate threats, 2 separate timelines, one planet in the middle, and to understand why 2026 specifically produced this combination, and why it will keep producing similar combinations through the rest of the year, requires understanding where the sun sits in its own 11-year rhythm. Because solar cycle 25 was supposed to be quiet, scientists predicted it would be weak. It was anything but. The coronal hole and AR 4436 are both solar threats, but they work in completely different ways. Understanding the difference matters, because each one requires a different kind of preparation, and each one's damage potential follows a different logic. A coronal mass ejection is a bullet. When a sunspot like AR 4436 erupts, it fires a concentrated cloud of magnetized plasma into space. That cloud is enormous, often stretching millions of miles across, but it travels in a specific direction. If Earth is in the path, it takes a direct hit. If Earth is off to the side, the cloud passes by. The difference between a catastrophic storm and a near miss can be a matter of degrees in the ejection's launch angle. The cloud travels at speeds between 200 and 2,000 miles per second, depending on how energetic the eruption was. It arrives at Earth anywhere from 15 hours to a few days after launch. When it hits, the impact is sudden and concentrated. The magnetic field embedded in the cloud can be extremely strong, and if it turns southward, can drive the most intense geomagnetic storms in the record. The G5 Quebec event in 1989 came from a coronal mass ejection. A coronal hole high-speed stream is a floodlight. It doesn't fire in a specific direction at a specific moment. It streams continuously along open magnetic field lines, sweeping past Earth for days as the sun rotates. The stream isn't as concentrated as an ejection cloud. It spreads out as it travels. The magnetic field it carries is usually weaker than a direct ejection impact, but it lasts longer. The May event kept conditions elevated across 2 days. The other key difference is predictability. Because coronal holes rotate with the sun, their streams can be forecast with reasonable accuracy days in advance once the hole is detected in an Earth-facing position. Coronal mass ejections, on the other hand, are sudden. They happen when a sunspot erupts without much warning. Forecasters can watch a complex sunspot region and say the probability of an eruption is elevated, but they can't say exactly when it will happen, or exactly where the ejection will go. R4436 was the unpredictable threat. The coronal hole was the foreseeable one, both active at the same time, and here's the context that ties both threats together. The current phase of solar cycle 25 is specifically the phase where this combination becomes more common, not less. Because the solar maximum is over, the sun is entering its declining phase, and in the declining phase, coronal holes multiply. They persist longer, they drift toward the equator, and active sunspot regions like AR 4436, while they become less frequent than at peak, can still be dangerously complex. The nature of the solar threat is shifting, and most people don't know the cycle even exists. Imagine a lighthouse sitting 93 million miles away. Its beam sweeps around once every 27 days. Every time it sweeps past Earth, the same stretch of ocean lights up. Then the beam moves on. 27 days later it comes back, same stretch, same light. That's how a coronal hole works. The sun rotates once every 27 days as seen from Earth. A coronal hole rotating with it sweeps its high-speed solar wind stream through the inner solar system like a lighthouse beam. Earth, orbiting the sun in a fixed track, sits in the path of that beam once per solar rotation. If the coronal hole survives, Earth gets hit again. This recurring behaviour is one of the most useful properties in space weather forecasting. Unlike a coronal mass ejection, which fires once and is gone, a persistent coronal hole produces a predictable rhythm. Space weather agencies can look at a storm event caused by a coronal hole and mark the calendar 27 days forward as a watch date for a potential repeat. The May 13th coronal hole event produced G2 conditions on May 15th and 16th. 27 days forward lands in mid-June 2026. Forecasters at the Space Weather Prediction Centre and the Australian Space Weather Forecasting Centre confirmed this recurrence logic applies, but left the outcome labelled as theory and unknown. Whether the hole will still exist in mid-June and whether it will be large enough to produce similar effects depends on whether the magnetic configuration that created it stays open that long. Coronal holes can persist for weeks to months. Some survive multiple solar rotations. Some shrink and disappear within days of being detected. The magnetic structure that keeps the field lines open is not static. It can close over time. The size of the May coronal hole was described as pretty large by automated detection systems. Large holes tend to persist longer. The equatorial positioning means it stays aimed near Earth's orbital plane throughout its rotation. Both factors slightly increase the probability of a return engagement. But slightly is the operative word. Whether this specific hole comes back around as a meaningful storm driver in June is genuinely unknown at the time of the May event. What is known is that the Sun is entering a phase where this lighthouse pattern becomes the dominant space weather story. Fewer dramatic one-time eruptions, more recurring, rotating coronal hole streams making passes at Earth every 27 days. And understanding why requires understanding what phase of its 11-year cycle the Sun is actually in right now. Because the timeline here was supposed to look different. Scientists had a prediction. Solar cycle 25 was supposed to be quiet, manageable, below average. The Sun had other plans. Every 11 years the Sun goes through a complete magnetic cycle. Sunspot activity rises from a quiet minimum to an active maximum, then falls back toward minimum again. At maximum, the Sun's magnetic field is tangled and stressed. Sunspots cluster, flares fire, coronal mass ejections launch toward the planets. At minimum, the field is cleaner, fewer sunspots appear, and space weather calms down. The current cycle, Solar Cycle 25, officially began in December 2019 when the Sun reached its last minimum. Forecasters from the Solar Cycle Prediction Panel looked at historical patterns, studied the Sun's behaviour in the cycles leading up to this one, and issued a prediction. Cycle 25 would be average to below average. The smoothed monthly sunspot number, the standard measure of solar activity, would peak somewhere between 105 and 125. The Sun ignored that prediction entirely. By February 2024, the smooth sunspot count had already reached 137 and was still climbing. The actual solar maximum, the peak of the cycle, is now confirmed to have occurred around October 2024. The final peak number exceeded expert projections significantly. Cycle 25 became one of the strongest solar cycles in recent decades, despite being forecast as modest. Why did the models miss? The short answer is that predicting solar cycles requires understanding deep processes inside the Sun that remain only partially mapped. The Sun's internal magnetic dynamics, the mechanisms that generate and destroy sunspot activity, are confirmed to exist but are complicated enough that even the best models carry significant uncertainty. The mistake didn't cause harm. It caused a pleasant surprise for Aurora watchers and a busy period for space weather agencies. But it's a reminder that solar science, advanced as it is, still operates with real gaps. As of May 2026, the Sun is in the declining phase of Cycle 25. The maximum is behind it. The smooth sunspot count is falling. The number of active regions producing X-class flares is declining. But here's the part that catches most people off guard. The declining phase is when coronal holes become more common, not less. During solar maximum, the Sun's magnetic field is so tangled that closed magnetic loops dominate the corona. The high-energy regions produce big flares and ejections, but as the field relaxes toward minimum, open field regions, coronal holes, start appearing more frequently, especially at lower latitudes near the equator. They persist longer, they aim more directly at Earth. The nature of the threat changes, from dramatic sudden events to steady, recurring streams. For the rest of 2026 and into 2027, coronal hole high-speed streams will increasingly define the space weather environment. AR4436 style eruptions will still happen, but the sustained rhythm of the rotating coronal hole lighthouse will be the background hum. and the models predicting that rhythm just got a major update. Because a European mission discovered something about solar wind near the sun's surface that no existing forecast model had accounted for. Something that changed the numbers everyone was using. When solar cycle 25 ended up stronger than predicted, scientists went looking for an explanation. The historical record goes back over 300 years of sunspot observations and about 70 years of satellite data. Forecasters use that data to build models of how each new cycle will behave. They look at the strength of the sun's polar magnetic field at solar minimum, which is a reliable proxy for how active the next cycle will be. They look at patterns in previous cycles. Cycle 25 had a relatively weak polar field at its minimum. That's why the prediction called for a modest cycle. The weak polar field usually means fewer sunspots. The actual outcome surprised nearly every modelling team. One factor that emerged from post-maximum analysis was the role of small-scale magnetic features on the sun's surface that older models didn't weight heavily enough. These features, called ephemeral active regions, appear and disappear quickly, but contribute to the sun's overall magnetic energy budget. Models that included them more accurately tracked Cycle 25's stronger than expected rise. This isn't a crisis in solar science, it's an update. Models improved. Predictions for Cycle 26 will incorporate these features more carefully. But the lesson matters for how people think about space weather preparedness. The 2 decades between solar maximums don't produce a constant level of risk. The nature of the risk changes through the cycle. Maximum brings intense but sporadic events. Declining phase brings persistent, recurring coronal hole streams. Minimum brings a quiet period, followed by the first stirrings of the next cycle's sunspots in the opposite hemisphere. For 2026, the calendar says declining phase. The coronal holes say so too. The May 13th hole is exactly the kind of equatorial persistent structure that characterises this part of the cycle. And while solar cycle 25's maximum was a surprise on the upside, the forecasting models that missed it were also missing something more fundamental about how solar wind actually works near the sun. Something a European spacecraft team only discovered in April 2026. Something that showed the wind moves 4 times faster near the sun than anyone thought. And that single finding means every existing space weather forecast model is working with incomplete numbers. To understand solar wind near the sun, you need to see a region that's almost impossible to observe. The inner solar corona, the part of the sun's outer atmosphere closest to its surface, is normally invisible from Earth. The sun itself is so blindingly bright that its light floods the nearby space, overwhelming any instrument trying to see the faint structures just above the surface. Scientists have long known extraordinary things happen in this zone where solar wind forms and accelerates, but directly imaging it from Earth or from most satellites is impossible. The solution, in theory, was simple. Block the sun's disk completely. Observe what's around it. Solar eclipses do this naturally. But they last minutes, occur at specific ground locations, and can't be predicted with enough frequency or controllability to build a research program around. So the European Space Agency built an artificial eclipse. The mission is called Proba 3. 2 small spacecraft launched into orbit flying in precise formation 150 meters apart. One spacecraft carries a disk designed to block the sun's light. The other spacecraft, positioned exactly behind the first, sits in the shadow of that disk. From the second spacecraft's perspective, the sun is perpetually eclipsed. The corona glows around the black disk of the first spacecraft. 150 meters of separation across the distance of space. The 2 craft maintain that gap to within millimeters. The observations Proba 3 conducted in early 2026 produced results that overturned a key assumption in solar wind science. Scientists had estimated that the slow solar wind, the quieter background stream that fills space between faster coronal hole streams, travels at around 60 miles per second just above the sun's surface. That number came from models and from indirect observations because the inner corona had never been imaged in sustained detail at this scale before. Proba 3 measured something different. The solar wind close to the sun's surface was moving at nearly 300 miles per second, not 60, 300, 5 times faster than the models assumed. The wind accelerates much more rapidly and much closer to the Sun than any existing model predicted. And that finding has direct consequences for predicting when solar wind from events like the May coronal hole will actually arrive at Earth. The numbers from Proper 3 were published in April 2026. Scientists studying solar wind acceleration had long known the wind speeds up as it travels away from the Sun, but the precise location and rate of that acceleration was uncertain. Models assumed the bulk of the acceleration happened farther from the Sun, at distances where observations were more reliable. What Prober 3 showed is that the acceleration happens much faster and much closer in. Near the surface of the Sun, the slow solar wind component was moving at approximately 300 miles per second. The models had assumed around 60 miles per second for slow wind at that distance. The discrepancy is enormous. The actual speed is roughly 5 times higher than the assumed baseline in models. For the faster wind from coronal holes, the implications extend further. If the baseline slow wind is already moving faster near the Sun than models assumed, then the interaction between the fast coronal hole stream and the slow background wind that forms the co-rotating interaction region happens differently than predicted. The wall of compressed particles forms at a different location. It develops different properties. Every space weather forecast model that predicts when a solar wind stream will arrive at Earth, and how strong it will be, is built on assumptions about how the wind behaves near the Sun. Prober 3 showed those assumptions were significantly off. This is a confirmed limitation. Scientists acknowledge it directly. The models need updating to incorporate the new near-Sun velocity data before their predictions for coronal hole stream arrival timing and intensity can be considered accurate. For the May 15th event, this meant that the forecast of G2 conditions carried an acknowledged uncertainty beyond the usual BZ unpredictability. Even the arrival time calculation had margins that existing models couldn't fully close, because they were using a number for near-Sun solar wind speed that Prober 3 proved was wrong. Space weather forecasting is better than it has ever been. The tools, the satellites, the models, the data, all of it has improved dramatically since the 1989 Quebec event. But Prober 3's finding is a reminder that even well-established scientific frameworks can carry fundamental errors for decades, simply because the observations needed to test them weren't technically possible until now. The Sun has been moving its wind faster than Earth's best models knew. For how long? Since the models were built. And while scientists work to update their understanding of solar wind near the Sun, a question that sounds almost unscientific was lurking at the edges of the space weather discussion. Does a geomagnetic storm affect the people living under it? The data on this is strange, and what it shows is harder to dismiss than most people expect. Here's what the Prober 3 discovery means in plain terms. Every time a space weather agency issued a forecast for the arrival of a solar wind stream, that forecast was calculated using software that assumed solar wind near the Sun travelled at around 60 miles per second in its slow component. The actual speed was around 300 miles per second. The models were off by a factor of roughly 5 near the Sun's surface. Now, solar wind does decelerate and stabilise as it travels farther from the Sun, so the error doesn't scale perfectly across the full 93 million miles. The wind speed at Earth's orbit is measured directly by monitoring satellites and is accurate. But the predicted timing of arrival, which depends on modelling how the wind behaves across the full journey, carries the error of the wrong starting assumption. For most practical forecasting, this uncertainty lands within a window of a few hours, which is tolerable for Aurora viewers planning an evening outside, but matters more for satellite operators and grid engineers trying to time their protective measures precisely. The deeper issue is what Prober 3's finding suggests about our overall understanding of solar wind formation. The inner corona is where the wind is born, where magnetic energy is converted into particle kinetic energy, and where the properties of the stream are set before it ever reaches Earth. If the acceleration in that region is fundamentally different from what models assumed, then other properties of the wind, its temperature, its density profile, its magnetic field structure, may also behave differently than current models predict. Scientists confirmed the Proba 3 finding represents a required update to existing models. Preliminary work on incorporating the new velocity data was underway by the time of the May 2026 events, but fully recalibrating and validating a new generation of forecast models takes years. The technology for detecting and responding to space weather is better than at any point in history. The theoretical foundation underneath that technology just discovered it needed revision. For the May 15th coronal hole event, forecasters worked with the best available models, knowing those models carried this acknowledged gap. The forecast of G2 conditions was still the best available estimate. It was still more useful than nothing by a large margin. But behind every precise number in the forecast, a quieter uncertainty sat unresolved. And while scientists worked to close that gap in their models, a separate question about the storm's effects was generating discussion in a different scientific community entirely, one that studies biology, one that studies people. To understand what the May event might bring, forecasters looked back at the last comparable event, February 17, 2026, a coronal hole positioned near the Sun's equator, high-speed stream aimed at Earth, the compressed wall arriving first, BZ dropping to -7 nanoteslas on the southward side, G2 conditions confirmed. The sequence was nearly identical to what was projected for May 15th. During the February event, the southward Bez flip drove sustained magnetic reconnection at Earth's dayside magnetopause. Energy poured into the magnetosphere. The auroral oval expanded to geomagnetic latitude 55 degrees. Northern Scotland lit up. Scandinavia reported vivid displays. Power systems in high latitude regions registered voltage fluctuations. Satellite operators reported increased drag corrections. No transformers failed. No blackouts occurred. The G2 level meant elevated effects, careful monitoring, some disruption, but no catastrophic outcome. That February event became the benchmark for May. Forecasters looked at the coronal hole size, the projected wind speed, the expected KP index, and compared each variable to February's numbers. The structures were similar enough that the February outcome provided a reasonable reference point for what May might look like if B's behaved similarly. The unknown remained the same. BZ, its southward extent and duration during the May event's compressed wall arrival, would be the deciding factor between a storm that mirrored February or one that escalated beyond it. This process of using past events as benchmarks is standard in space weather forecasting. Each major event adds to a database of real-world outcomes matched to solar conditions. Over time, the database improves the reliability of future forecasts. The February event was well documented. The May event had good analog coverage. But there's a part of these storm events that the scientific database covers less completely. A part that sits at the intersection of space physics and medicine. A pattern that researchers have documented statistically but struggle to explain mechanistically. The effect of geomagnetic storms on the people living under them. It sounds like ancient superstition. The data says something else. 27 days after May 15th lands in mid-June 2026. That's the date on space weather watch lists. That's when this coronal hole, if it survives another full solar rotation, sweeps back into an Earth-facing position and potentially fires another high-speed stream in Earth's direction. Whether it comes back as a meaningful threat depends on whether the hole still exists, and whether it does is genuinely unknown. Coronal holes are defined by open magnetic field lines projecting outward instead of looping back to the Sun's surface. That open configuration can remain stable for weeks to months if the magnetic region maintaining it stays in place. Some coronal holes have been tracked through 3 or 4 full solar rotations, showing up as a new storm driver each time their 27-day cycle lines up with Earth. Others close within days of being first detected. The magnetic structure that keeps the field lines open weakens. Surrounding closed-loop regions push in. The hole shrinks, tightens, and eventually disappears. Scientists can observe the hole's current state continuously through the Solar Dynamics Observatory's ultraviolet cameras, but predicting whether the magnetic configuration maintaining the hole will remain stable for another 4 weeks requires modelling the Sun's deep magnetic processes, which remain partially understood. For the May hole, the factors that made it initially significant, its large size, its equatorial position, its confirmed output of elevated solar wind, are also the factors that suggest it could persist. Large holes tend to be supported by stronger, more stable open field regions. Equatorial positioning means the configuration sits in a more magnetically active zone. The Australian Space Weather Forecasting Centre confirmed the recurrence logic applies to this class of event, but they also confirmed the mid-June scenario as a theory, not a certainty. What is certain is that even if this specific hole closes, the Sun in its current declining phase will produce new equatorial coronal holes with similar properties. The lighthouse beam might shift to a slightly different position. The rhythm continues. For the rest of 2026 and into 2027, Earth will continue absorbing recurring high-speed stream impacts. Some will be G1 events, barely noticed. Some will be G2 events like May 15th. And statistically, at least one or two may hit harder if the magnetic conditions align. Each event adds data. Each event tests infrastructure. Each event reminds engineers and policymakers that the space weather threat is not hypothetical. But one question that these events raise is rarely discussed in official forecasting documents. It shows up instead in peer-reviewed medical journals and epidemiology studies. And the pattern those studies found is harder to explain than the Aurora or the GPS disruption. It's about what geomagnetic storms do to biological systems, specifically to humans. This is the part of space weather science that makes physicists uncomfortable. The story so far has been clean physics, magnetic fields, charge particles, atmospheric chemistry, satellite drag. These are well-understood systems with well-measured effects. What some researchers started tracking in the 1980s and confirmed in statistical studies through the 2000s and 2010s is something different. A correlation between elevated geomagnetic activity and measurable changes in human biology. Here's what the data shows. Multiple peer-reviewed studies, using hospital records, health monitoring databases, and controlled biological measurements, found correlations between geomagnetic storm periods and specific health metrics. Heart rate variability, a measure of how well the heart adapts to changing demands, showed changes during geomagnetic active periods in some study populations. Some epidemiological datasets showed slightly elevated cardiovascular event rates during G2 and G3 storm windows. A smaller body of research found correlations with mood and sleep disturbance in sensitive individuals. The correlations are confirmed as statistical patterns. The mechanism that might explain them is unknown. This is an important distinction. A statistical correlation between two events doesn't prove one causes the other. Humans are complex biological systems embedded in an environment full of changing variables. Establishing that geomagnetic activity directly causes heart rate changes in a biologically clear causal chain has not been achieved. What scientists confirm is that the Earth's magnetic field changes during storms. The field we live inside every day, the same one that deflects solar wind, is also the background magnetic environment that human biology evolved within. Some organisms clearly use it. Birds navigate by it. Sea turtles use it for migration. Certain bacteria orient to it. Whether humans have any biological sensitivity to the field's fluctuations is a theory. A theory backed by statistical data, but still a theory. The effects, if real, are subtle. Space weather agencies do not list human health as a confirmed impact category at G2 levels. The effects are considered at most statistically detectable in large populations, not individually dangerous. So during the G2 conditions on May 15th and 16th, the people watching auroras in Montana and Scotland were probably not being harmed in any meaningful sense. Their GPS was less accurate, Their radio might have had static. Their power grid was being carefully managed in the background, and possibly, in some studies' findings, their sleep that night was slightly lighter than usual. The confirmed impacts of a geomagnetic storm are technological. The biological question remains open. But while that biological question stays in the realm of theory, the technological question has a very clear and very alarming upper boundary. Because G2 is manageable, G5 is not. And the question of whether Earth could survive a G5 today deserves an honest answer. In 1989, a G5 geomagnetic storm took down the entire Quebec power grid in 90 seconds. 6 million people lost power. The blackout lasted 9 hours. Transformers failed across North America and Europe. The event cost billions of dollars, and by the standards of solar history, it wasn't even the worst the sun has ever produced. In 1859, a storm now called the Carrington event reached an intensity that no modern instrument has ever recorded. Auroras appeared over the Caribbean. Telegraph operators reported their equipment sparking and catching fire. The induced currents in telegraph lines were so strong that some operators disconnected their batteries and kept transmitting on solar-induced current alone. The Carrington event is estimated to have been a G5 at minimum. Some analyses suggest it was stronger than anything on the modern scale. Scientists estimate an event of Carrington magnitude has roughly a 1 in 150 chance of occurring in any given decade. That sounds rare. Over a 50-year window, the probability climbs significantly. Here is what a Carrington-scale event would do to the world of 2026. High-frequency radio communication would collapse globally. The entire sunlit side of Earth would lose contact. Aviation, maritime, military, emergency services, all dependent on radio for backup communication, would go dark. GPS satellites would be severely disrupted for days to weeks following the storm. The satellite infrastructure, from navigation to financial transaction timing to power grid synchronization, would experience cascading failures. Power grids at high latitudes would face the most immediate threat: transformers overheating from sustained geomagnetically induced currents could fail in large numbers. A large high-voltage transformer takes months to replace. It weighs hundreds of tons. It's custom manufactured. There are only a handful of factories worldwide that build them. A cascading failure across multiple transformers in interconnected grid regions could leave parts of North America, Europe, and Asia without power for months, not hours. Satellites in low orbit would see atmospheric drag increase dramatically. Some would lose altitude faster than operators could compensate. In 2026, the world is more dependent on the systems that space weather attacks than it was in 1989. More satellites, larger grids, more GPS-dependent infrastructure, more digitally coordinated supply chains. The exposure is larger. The May 15th event was a G2, manageable, documented, handled. But every G2 event is a rehearsal. Every Aurora over Montana, every voltage alarm in a Canadian substation, every GPS error over a polar flight path, every satellite orbit correction, every radio blackout over Iceland. Those are the small-scale version of the same physics that could, on a different day, with a different coronal mass ejection on a different trajectory, produce the largest disaster in recorded human history. The sun is a star. It does not negotiate. It does not warn. It does not aim. A hole opened in it on May 13th, 2026. Earth felt it 2 days later. The lights danced over Scotland, and the sun kept burning.